I guess it's time to begin. Thanks for coming. I think I'm supposed to say some things about the conference itself. So this conference is the Seoul-Tokyo or Tokyo-Seoul Conference. Has been going on for quite a long time. I think more than about 20 years, I think. So the hosts institutes are usually KIAS and the University of Tokyo. So next year will be at Tokyo, if there will be. This year's theme is mathematical physics in general. It's quite broad, I think. And our first speaker is Dr. Anderson Vera at IBS Center for Geometry and Physics, Pohang.
Okay, thank you very much for the introduction. And thank you very much to the organizer for giving me the opportunity to talk here. So the framework of this talk is quantum topology. And so the topic of this year is mathematical physics. So this quantum topology has some motivation in mathematical physics. Of course, I don't understand that well, but I will start like some historical background telling about this, how this arises from mathematical physics. And this will be the first part. In the second part, this could be a little more technical part. This is about some algebraic invariants that we can associate to a surface. And in the third part, I will explain this. This is famous quantum invariant introduced by Le-Murakami-Ohtsuki for closed three manifolds, but this can be extended to three manifolds with boundary. And in this case, it's called the LMO functor, which was introduced by Cheptea-Habiro, which unfortunately is not here today, and Massuyeau. And in the last part, I will explain how, like, an idea how this quantum invariant can be related with algebraic invariants. So in some sense, this part is like a classical topology part, and this is like quantum topology part. So we can relate sometimes these two approach to topology. So I guess that maybe the background of all of us is a little bit different. So this part will be, I will try to be very, like, I will start with very basic things. So let me start. So the fundamental question in topology, or in general in mathematics, is like, how can we distinguish two objects of the same nature? So for instance, in knot theory, so given two knots, so embeddings of S1 into a three-dimensional space. And the question is if they are different. And in general, this kind of question could be very difficult to answer. So in this case, these two knots, they are not different. And this is because we can deform one into the other by some kind of combinatorial moves. So, or in the three-dimensional space, we can move topologically. So here we have the picture of this, for instance, how can we do in this case? So we start with one of the knots, and we can take this part here and make it bigger. And then we can take it to the other side. And then we stretch a little bit, and we obtain the second figure. So if two knots are the same, we can find this sequence of movements. But in general, so given two knots or two links, we can try to make the moves, and we cannot arrive, because in finite time. So we could expect that the knots or links are different, but we need to prove. So let me give an example. So here we have these two links. So we have two copies of S1 embedded in the three-dimensional space in apparently different ways. And we do the same question. Are they different? And in this case, the answer is yes. But as I said, we could start to try to deform this one into the second one. And we try many times, many hours, and we see that is not possible, that it seems that it's not possible, but we want to prove it. And to prove it, so the classical idea, not only in mathematics, but not only in topology, but in general in mathematics, is to construct invariants. So some kind of quantities that are easier to compare. For instance, in this case, for these two links, there is one basic invariant which can distinguish these two links, and this is the linking number. So let me recall. So for some of you, it's maybe very familiar. So if we have the diagram of the knot in the plane, it's oriented, so link. So we have two components at least, like a red component and blue component. And in the diagram, we could have two kind of crossings. So this kind of crossing, which we call positive crossings, and we associate +1. Or we can have this kind of crossing. And this we associate -1. And then we associate this number, like we take the sum over all the crossings. We take 1/2 of this quantity, and this is an invariant. So this is an invariant of links. It's very easy to compute. And in this case, it works to distinguish these two links. So here we have two crossings of this kind. And here we have 6 crossings. And there are 3 positive crossings and 3 negative crossings. So they will cancel in this case. So in this case, if we compute, we will find that the linking number is 0 for this link. And in this case, the linking number is -1. And of course, we can now, so comparing the two knots is difficult, the two links is difficult, but of course, comparing 0 and -1 is easy. So we can conclude that the two links are effectively different. And in topology, or mainly in quantum topology has some characteristic, and is that only works like in dimension 1, like for knots and links. In dimension 2 for surfaces, but not for surfaces itself, but for the symmetric group of surfaces. So for the what we call the mapping class group. So we don't compare surfaces because we have classification of surfaces, but what we want to distinguish is two different symmetries of the surface. And we have the three-dimensional case, so three manifolds or cobordism. So three manifolds, closed three manifolds, or three manifolds with boundary, but the boundary we want, like the boundary is good enough. Like we can split the boundary in some canonical way. So one intuitive idea is like we take a surface and this surface is changing on time. So this creates a cobordism. So these are the three main kind of objects that we work in quantum topology. Some people have tried four-dimensional case, but in general, these invariants in four dimensions, they can be recovered from algebraic topology. So they are, until the moment, it's not so interesting to go to higher dimension. So so this quantum invariant, so this start with the Jones polynomial in the 80s. So this was very different, like the new kind of invariant for knots. And it was almost like a coincidence that Jones discovered this invariant. So he was working in functional analysis, and he found that there are some representation of the break group. There are some representation, but he presented that work in a conference, and there was some not theorist, Joan Bierman, and she suggests that it's very similar to the break group. So he worked on that, and he defined this polynomial, which is very powerful and is the starting of quantum invariance. So after this, Witten, so this is like the physical origin, like Witten, he took the work of Jones and he gave an interpretation of this work by using some ideas from physics. And this interpretation allowed him to propose invariants of three manifolds. But so the approach of Witten is using some kind of Chern-Simons path integral. So this is an integral over an infinite dimensional space. So this is not mathematically well defined. But at that time, so it was like, this motivated a lot mathematicians to work on this. So people tried to understand how can we define these invariants from Witten from a rigorous mathematical point of view. And for this, there were basically two approaches. So one approach is the so-called non-perturbative approach. This was by Reshetikhin and Turaev. And in this approach, what they do is that instead of taking this integral over an infinite dimensional space, they take some finite linear combinations of quantum invariants of knots. So basically, they take like linear combinations of Jones polynomials, several Jones polynomials. So this was Reshetikhin and Turaev, but also like at that time, similar time, Turaev, he also working with Biro, he also developed this technique not only for knots, or not only for three manifolds using knots, but also for three manifolds using tetrahedron. So, and this is what we call Turaev-Biro invariants. So we have this kind of two families of invariants, Reshetikhin-Turaev, we are basically based on knots, and Turaev-Biro, which are basically based on a tetrahedron. And this kind of invariants, so both of them, they can be extended to three manifolds with boundary. And this, when we extend to three manifolds with boundary, they are good enough such that we can glue. So if we glue three manifolds along the boundary, this invariance behaves well. And this is what people call a topological quantum field theory. In the perturbative side, almost like 3 years later, after Reshetikhin-Turaev, so the idea is that by using some ideas from physics, this kind of integrals can be interpreted like we can take some kind of asymptotic expansion. And in this asymptotic expansion, there are some sums indexed by diagrams. These are called Feynman diagrams. And then, so this is still like at the mathematical physics level of rigor, but in the purely mathematical side, this was developed by Kontsevich, and this gives rise to the Kontsevich integral. So this is invariant for knots or links. So this was like a big one of the, so Kontsevich had many big works, but this was one of the first, this was one of the works that he got the Fields Medal. And this invariant, so now this is for links, so we can also generalize for three manifolds. And this is the Le-Murakami-Ohtsuki invariant. This is for closed three manifolds. And when we extend to the three manifolds with boundary, this is the Le-Murakami-Ohtsuki functor. And this was introduced by Cheptea-Habiro-Massuyeau. I don't know, Habiro maybe is in the Zoom. Habiro Sensi. So this is that I will try to explain the main ideas of this invariant. But first, I will go to a little more technical part, and it's the classical topology part. And are there any questions so far in the first part? So this is a little bit technical, but the idea to keep in mind is that given a surface, we can associate some algebraic invariants to the symmetric group of the surface. So let me give some notations. So we have a surface, genus G surface, with one boundary compact oriented genus G surface. And we want to fix a system of meridians and parallels on the surface. So this will give us a basis for the fundamental group and also for the first homology group. And from the three-dimensional point of view, we want to consider this surface as the boundary of a handle body. So this is so we have like a solid genus G torus. So the boundary is the surface sigma and some disk. And this we keep the image of our system of meridians and parallels. So the image of the meridians, they become trivial on the handle body. Now, natural algebraic objects that we associate to topological spaces. So we have the fundamental group of the surface. This is generated by the homotopy classes of meridians and parallels, and the first homology group, which is generated by homology classes of these curves. We do the same for the handle body. So we associate the fundamental group. In this case, it's generated only by the longitudes or parallels, and the first homology group, which is only generated by the blue curves, the homology classes of the blue curves. And this map, this embedding, allows us to define some subgroups. So we have like the induced map in homotopy, and we take the kernel. So this is I denote by A bolt. And if we do the same, but in homology, we have this subgroup A. Of course, so if we take the abelianization of this one, it gives this one. And our group, like the group of orientation preserving homeomorphisms of the surface up to isotopy, or mapping class group, we denote by calligraphic M. And we have the similar group for the handle body. So the mapping class group of the handle body. And this can be identified with a subgroup of the mapping class group of the surface. So if we have an homeomorphism of the handle body, we can restrict to the boundary. So this gives an element in the mapping class group. And we can identify precisely which is this subgroup. This is not trivial fact. So this uses some classical result in topology, the Waldhausen theorem. So we have these two groups, and we have all these algebraic, also these groups. And we want to define invariants or algebraic invariants for elements in this mapping class group. So before that, let me give some other subgroups that we have in the mapping class group. So these subgroups, all of them are defined by using some conditions in the previous groups. So we have what is called the Lagrangian mapping class group. So this is like the elements in the mapping class group which are preserving the meridians. And we have the Torelli group, and these are the elements in the mapping class group which are the identity in homology. This is the most studied subgroup of the mapping class group. And we can define an analogous of this Torelli group, but for the Lagrangian mapping class group. So these are the elements which are the identity only in this subgroup A. So they are the identity on the meridians. And we have one more Torelli kind group, a little bit more complicated. This was introduced by Habiro and Massuyeau. But the idea is always the same. So Torelli kind groups are like some kind of elements which induce the identity on some quotient. So for instance, here we have like the condition is that on the fundamental group, the elements induce the identity up to some subgroup K2. And this K2 is this group. So generated by like the meridians on the homotopy case and commutators of pi. So we use K2. We are thinking in this as a weight. The 2 is like weight, and we see the meridians as having weight 2. And there is a second condition. But this condition is also like some kind of, so they are inducing the identity, but only for K2, and in this case up to K3. And K3 is like elements of weight 3. So we have commutators of length 3, normal commutators, but we can have commutators of length 2, but one of the elements is in this subgroup A, which is weight 2. This is a little bit more technical, but I will come back to this group later. We can have some examples of elements in these subgroups. So we have a simple closed curve on the surface, like this alpha 1, 2, going around the first handle and second handle. So to any simple closed curve, we can associate one symmetry of the surface. It's called the Dehn twist. So we take a neighborhood of the curve. So this is a cylinder of annulus. And we cut along the curve, we twist, and we glue again. So the action, for instance, on this green curve is like it twists the curve. So this is called the Dehn twist. So if we take the Dehn twist along this curve, this is an element of the alternative Torelli group, also of the Lagrangian Torelli group, but it's not in the Torelli group. So this element, the Dehn twist along this curve, does not act trivially on homology. So we can see, for instance, the action on B1 is non-trivial. And in general, this is like the lattice of subgroups that we have. So we have the Lagrangian mapping class group. We have these three kind of Torelli groups. We cannot compare the Torelli group and the alternative Torelli group. But the intersection is non-trivial, and it contains some important subgroup of the mapping class group, which is called the Johnson subgroup. So this group is like the group generated by Dehn twists along curves which are separating. I will come also later to this group. And then, so these groups is like the first step. So we have mapping class group. We want to study the mapping class group. The first thing that we do is we study the action on homology. So this is like linear algebra part. And then we go to the next groups. And these are the next groups, the the Torelli kind groups. But this will be like the first step. So we want to go further. So this will give rise to some filtrations of the mapping class group. And to define these filtrations, we need the notion of to recall the notion of the lower central series. So we have a group G. The lower central series is this sequence. So the first term is the group itself. The second term is commutators of length 2. And the third term is commutators of length 3, and so on. So the Johnson subgroup, it will be a sequence of subgroups. It starts with the Torelli group, the Johnson filtration. And the M term in this filtration is like elements which act like the identity up to the M+1 term in the lower central series of the fundamental group of the surface. So in some sense, that this is like we approach the elements which act trivially in homology, but step by step by using the lower central series. And one key property of this, this filtration, so all these elements are non-trivial, but if we take the intersection, it becomes trivial. Now for the Lagrangian Torelli group, there is a similar filtration. This was introduced by Levin. And it's very similar to the previous one. But now we will use the handle body group. So we will use the information of the handle body. So this will be this sequence of subgroups. And the condition is like, so we have some kind of action like the identity, but at the level of the fundamental group of the handle body. And in this case, this filtration, so the intersection is non-trivial. So it's very big group. It's the intersection of the handle body group with the Lagrangian Torelli group. So this is very big group. So, but from the three-dimensional topological point of view, this is very good group because, so this group, like if we take any element in this group and we attach two handle bodies, so when we do this, we obtain a trimanifold. So if we take any element in the mapping class group, we can attach two handle bodies to obtain a trimanifold. But when we take elements in this subgroup, the trimanifold that we obtain is the three-sphere. So this is like from the topological point of view, three-dimensional topological point of view, this is related with the three-dimensional sphere. So this filtration is very good to study trimanifolds. This one is also good to study trimanifolds. And this property is very good because we can define some kind of good topology on the filtration, induced by the filtration. Now the alternative Johnson filtration, introduced by Habiro and Massuyeau. So it will be a similar filtration. But now we use different series. So we want to act like the identity, but on different quotients of the fundamental group. And the series that we use is like very similar to the lower central series, but we make some kind of shifting. So first element is the fundamental group. Second element is like commutators of weight 2. So now the elements of the meridians are like weight 2. And in general, Km is like commutators of weight m. So it's very similar to the lower central series, but for instance, here in K3, we have commutators of length 2, but one of the elements belongs to A, at least. And so the M term of this filtration will be defined similar as the previous Johnson or Johnson-Levin filtration. So we have like some kind of identity action. So they act like the identity up to this this term in the filtration, in this filtration. And there is the second condition, so they will act like the identity for the elements in K2, but up to K2 plus M. So this filtration is very good. So like it's very similar to the Johnson filtration. So the intersection of all the elements is trivial, and all the groups that appear here, so they are non-trivial groups, but they are residually nilpotent. So the intersection of the lower central series is trivial. And we can compare. So we have three filtrations, and we can compare explicitly how they are related. The most interesting property is that the Johnson filtration and the alternative Johnson filtration, so we can compare in both sides. Like, so in one side we have like the alternative filtration at degree 2m is contained in the degree m of the Johnson filtration, and the degree m of the Johnson filtration is contained in the m-1 of the alternative Johnson. So if we consider the topology induced by the filtration, they will induce the same topology. So this is a very good property. But what we are interested is in this kind of homomorphism, Johnson type homomorphism. So for every element on the filtration, the three filtration that we have, we can define some homomorphism. And these homomorphisms take values in some abelian groups. So for Johnson, so we have the homology of the surface, H. We take the free Lie algebra generated by H. This is graded Lie algebra. So the first elements are elements of H. Second elements are like the wedge product of two elements of H, and so on. So this is an abelian group, and there is this subgroup. So precisely this subgroup is defined in this way. So it's like the kernel of the Lie bracket at degree m. So these groups was defined by Kontsevich, implicitly defined by Kontsevich. And there is an homomorphism. So we can define some homomorphisms from the Johnson filtration to this abelian group. And the key property of this homomorphism is that the kernel is the next term on the filtration. This can be done similarly for Johnson-Levin, but instead of using the homology of the surface, we use the homology of the handle body. So we have the same. So we have some group homomorphism, and the kernel is the next term in the filtration. And for the alternative Johnson, we also have similar homomorphism. But in this case, so we have the homology of the surface, and the generators are meridians and parallels. So we need to split the generators. So the meridians, they will be, so we take like the free Lie algebra generated by the parallels in degree 1 and meridians in degree 2. For instance, this is like the first term of this. So no, this is degree 1, elements of B. This is elements of degree 2. So we see that in the usual Johnson filtration, this will be also degree 1, but here is degree 2. So we shift a little bit. And there will be an homomorphism with the same property. So the kernel is the next term in the filtration. So these homomorphisms are very easy to compute. Like they are basically the action on the fundamental group. So let's see some examples of explicit computation. So we have these two curves. alpha 1, alpha 1, 2. And if we compute for the alternative Johnson homomorphism, first Johnson homomorphism, we will obtain this value. And of course, because we can compare the filtrations, then we can compare the homomorphism too. Now the most interesting part, so this is like technical part, but to keep in mind is that we have these algebraic invariants. Now these invariants can be interpreted by using some diagrams. This is also an idea of Kontsevich. So we have a vector space generated by trees, but these trees are only, so we have univalent vertices and trivalent vertices. And the trivalent vertices, they are vertex oriented. So this means that on every vertex, we have a cyclic order. And the univalent vertices, they are colored by elements of the homology or any abelian group. And we take this vector space up to some relations. So we have this antisymmetry relation. So this say that if we change the cyclic order, we need to add minus. We have this relation, IHX. So this is like some kind of Jacobi relation. And multilinearity relation. So this is, if we color by linear combination, we can split the colors. And in this space, we have 2 degrees. So 1 degree is the number of trivalent vertices. And a second degree is the alternative degree. So in this case, we count the elements in A with weight 2 and the elements in B with weight 1. And we need this factor here to normalize, but this becomes a degree on this space. So here we have some table of some examples organized by degree. So internal degree. So 0 trivalent vertices, 1 trivalent vertex, 2 trivalent vertex, 3 trivalent vertex. And in the rows, we have the alternative degree. Now, what is interesting is that we can take this space for H or for A plus B, and we can relate this space with the target space of the Johnson homomorphism. And the map is very beautiful. So we take any tree and we send to the sum over the univalent vertices. We take the color of the vertex, tensor the tree rooted at that vertex. So let me give an example. So if we take this tree, so we send to the sum. So we take here, for instance, these univalent vertices, this univalent vertex. So we have here A, and now we take this tree rooted at A. So it gives this rooted tree. And now we read this as a commutator. So this gives B prime B commutator, and then commutator with A prime. And we do this with all the univalent vertices. So this map is also implicitly introduced by Kontsevich. And this map is an isomorphism. So this is very good property. And this works in both cases, for the alternative case and for the usual case. And this means that since the Johnson homomorphism is taking values in this subgroup dm, so we can take the diagrammatic version. So this gives some diagrammatic interpretation of our algebraic invariants. Here we have an example. So for this homomorphism, we compute algebraically is this element. Then we get some diagrammatic interpretation. And now, so this was classical topology. Let me relate this with the Le-Murakami-Ohtsuki invariant. So this invariant, so is very sophisticated invariant. And so this is a functor. So the source category is some kind of three manifolds M such that the boundary, so the boundary is a cylinder. So the surface times interval. So this gives us two embeddings of the surface sigma on the bottom and on the top. Typical example that we want to consider is we take the trivial cylinder. In the bottom, we embed with the identity. And in the top, we embed with an element of the mapping class group. This is called like a mapping cylinder of construction. And the target category, so there are some kind of diagrams. So these are the Feynman diagrams. So similar to the previous kind of diagrams, but we also have loops. We can have loops. And we have the same relations. So it's the same relation as before. And now how we go from this side to this side. So the idea is like, so we start with a cobordism. We have the two embeddings of the surface on the bottom and the surface on the top. And we take the image of the meridians and parallels. So we fix this system of meridians and parallels. So this gives us some curves on the boundary of this three manifold. And we use these curves to glue two handles, or like avocado. So we attach along this curve a two handle. And when we do this, we can fill this hole. But when we do this, we want to follow the trace of the, so this is called the core of the two handle, and this is called the co-core. So we follow the co-core when we do this filling. So for instance, here we see that if we attach here and we fill this hole, this small segment becomes this one. And we do the same on the top. So this will give some knotted object, but there is still topology. So this is not standard cube. So next step is that we take some surgery presentation. So we can codify this topology by adding some knot or link. And then this will be in the standard cube, -1, 1 cube. So this is the first step. Second step is that we use some invariant for knots or links. And the invariant is the Kontsevich integral. This is already complicated invariant, but this invariant will give some diagrams. And we need to get rid of the knot. At some moment, we choose a knot, but there are many knots. So we need to get rid of this ambiguity. And this means several combinatorial operations, complicated combinatorial operations. But at the end, we will obtain this kind of value. So this is the value of the LMO functor. We take cobordism, and this will be the output. And this, so the main question is, what is the topological meaning of this invariant? So how can we interpret this invariant from a topological, like from classical topology point of view? For instance, we know that these numbers, they are related with linking numbers. This number, the coefficient of the theta graph, is related with some famous invariant, Casson invariant. And the coefficients of the trees, they are related with the Johnson homomorphism. So let me give an example. So we take our canonical example from the beginning. We make all these constructions, so gluing the two handles. We will obtain this knotted object, and we compute, and we obtain this value. And we see here that the diagrammatic version of the Johnson homomorphism appears. And this is not a coincidence, so this is true. So like we can prove this. So if we take an element in the Lagrangian in the M term of the Lagrangian filtration, and we made the cylinder construction, and we compute this quantum invariant. And in this invariant, we kill some diagrams. In particular, we kill diagrams with loops. So this still is very big series of diagrams. But the first non-trivial term that appears is the Johnson homomorphism, the Johnson-Levin homomorphism. Of course, there are more diagrams. We don't know the meaning. And this is also true for the alternative Johnson filtration. So the same. So we kill cycles. So here we need to kill some homological information. This is related with the meridians. So here we don't need to kill meridians, and we obtain the diagrammatic version of the Johnson homomorphism. So this is like the beginning of this. Start with the works of Heidegger and Masbaum. They interpret, so in the Kontsevich integral, they found that the trees are related with Milnor invariants. So in some sense, the Johnson homomorphisms are like the three-dimensional Milnor invariants. There are some relation. Similar, so this result is also true for the usual Johnson filtration. This was done by Cheptea-Habiro and Massuyeau. This is like a table, like how we read the result. So in the columns, we have the Johnson homomorphism. In the rows, we have the alternative Johnson homomorphism. And this upper diagonal is like the Lagrangian Johnson homomorphism. And more recently, the LMO functor was also used to prove very difficult problem in the mapping class group. So it was not known if the first homology group of the Johnson subgroup has torsion. And recently, not recently, like 2 years ago, Nosaki, Masatoshi Sato, and Masaki Suzuki, they used the loop part, not the trees, but the loop part, to find that this group has torsion. So the LMO functor is really powerful invariant, even if we cannot compute. So we cannot compute in general, but we can use to prove many things. And thank you very much for your attention. So you have some question, so you need to use the microphone. Yes.
The unit triangular graph, does that have anything to do with graph?
Webs like Cooper-Berg. Yeah, they are similar. So in the case of Cooper-Berg, they are like fat graphs. They are related. Like we can define, we can consider webs, and we can attach this kind of diagrams to webs. And this is like some target space for invariants of webs. So there are some relation, yeah.
Okay. Right. Would you like to be you are the who I think you have third term you did not meaning did not say meaning. But this no this oh yeah.
Here.
Yeah. Here's that's originating from as a non-quadratic thing, so terms.
So this is so in some sense this is like non-perturbative. Right. So every finite part is non-perturbative. Right. So only the complete series is like the perturbative part. So the perturbative part, the perturbative approach is like in some sense perturbative invariants. They contain all non-perturbative. So these invariants are universal invariants in the sense that for instance, any quantum invariant of knots or three manifolds can be recovered from this invariant. That is one of the reasons, because this is almost impossible to compute in general. For like the Kontsevich integral. Kontsevich integral is very powerful invariant for knots, but we can compute only for the trivial knot. And even this computation is highly non-trivial.
Okay, can I ask more? You are the relation between two-dimensional and three-dimensional. Now, how about can you generalize this between three-dimensional and four-dimensional in the sense of the four-dimensional of the construction of the four-dimensional? Can you walk out this one?
Not for this invariant, but people have done that for Reshetikhin-Turaev invariants. But like the invariant is interesting only for three manifolds. When we compute for cobordism between three manifolds, this invariant can be computed by using algebraic topology, like cohomology or homology. But this is not the case for three manifolds. So quantum invariants for three manifolds, they are really different from algebraic topology invariants. So we cannot, at least we don't know what is the topological meaning. So we have that. So we take some algebraic object, like a Hopf algebra or quantum group. We use this algebraic data to construct some invariant of three manifolds. And it becomes an invariant because some algebraic properties of the data. So it's an invariant. We compute, we get numbers, but in general, we don't know the topological meaning. So only very special case, we know that, this number is related with the cohomology or with the representation of the fundamental group, but only small cases. In most of the cases, we don't know the meaning of these numbers. They are very powerful because, for instance, Turaev-Biro, we can use Turaev-Biro to classify like 14 millions of different three manifolds. So they are very powerful and we can compute in computer, but we don't know the topological meaning.
Other questions?
Thank you.